Assalamu alaikum, dear students. I hope all of you are fine. Now let us start from where we left the last time. We were talking about orthogonal trajectories. You have a given family of curves. Then you have another family of curves such that at the points of intersection of these two sets of families, the tangents to the corresponding curves are orthogonal. So we call the second family the orthogonal trajectories of the first family. Now we have got a theorem which would be perhaps the last one in unit second. So it says that for a surface, parameters can always be chosen so that the curves of a given family and their orthogonal trajectories become the parametric curves. Means I can always reparameterize a surface such that my given family, a family of curves that I would start with, and its orthogonal trajectories become the parametric curves. So that means under those new parameters, let me call them u prime and v prime, ru dot rv prime dot under these new parameters should be equal to 0. And we know that it is the case if we take sort of plane and we take x vertical lines and natural enough, not so natural actually, vertical and horizontal lines on a plane, then they would form orthogonal trajectories, and they are also the parametric curves. And similarly, if I take the polar coordinates as my parameters, so then the lines through the origin and circles with center at origin form orthogonal. They are mutually orthogonal. Circles are the orthogonal trajectories of these lines through the origin. Okay, now to start with, now we want to start with a family of curves, an arbitrary family of curves, and then we want to show that there is no harm if I take that set of curves and its orthogonal trajectories as parametric curves. Okay, so let r equal to r at uv as usual be the equation of the surface and I take and let phi of uv, as we did last time when we discussed orthogonal trajectories, equal to some constant c, be the equation of a given family of curves. Be the equation of a given family of curves. Let's call this equation 1 and let's call this equation 2. Of course, it's a family of curves, as we already know. Last time I showed you that. Of course, now I have a surface. Which I denote here, and I have got its domain which lies inside our UV plane, right? So given a curve here, it corresponds to some curve here, right? And now I have chosen a family of curves here. It means I have automatically, via the map R, which sends these points onto the surface. So I have got a family of curves here. Now, phi of u we see is a family of curves here, which corresponds to a family of curves on the surface. I could have actually used xy plane, but that's no. We usually use uv as our parameters because xy can also be used as a parameters, but in a special situation when we have a Monge's form, when you can write z is equal to f of xy, then of course there is no harm in taking them to be x and y. And so, but I want to write it as a differential equation. So I differentiate and I get, when I differentiate, I will get phi sub u du plus phi sub v dv is equal to 0. So, and since it can be written in a more equivalent form, because what I want to derive a condition, what would be the differential equation of its orthogonal trajectory. So I take the most general way and I write it as, so it can be written, it is, let it be equivalent to, let it be equivalent to P du plus Q dv equal to 0. Of course, there are some functions of u and v, p and q, so that p would be lambda times phi sub u and q would be lambda times phi sub v for some lambda not equal to 0. Lambda is some function non-zero, and because right hand side is 0, so most general form of p and q would be this, right? Now you have to, we are going to impose the most general conditions. So p and q can be lambda times phi u and lambda times phi v. So which gives us du by dv is equal to minus, we know that, phi v by phi u. It is just the, you know about this now, when you write a function implicitly, then this is always true for a function, for the derivative of a function. So that would be, in this case, minus q by p, or in other words, du minus q is equal to dv by p. So which means that du and dv, these small changes in u and v, must be proportional to minus qp. In other words, which is the same thing as saying, therefore I can say minus q and p are the direction ratios, of tangent at any point, of tangent at any point of the family 1, of members of family 1, and uv of members of family 2nd, our family of curves. Family 2nd means phi of uv is equal to c. So I just take a little of words. Okay. Now what we do, now let the direction ratios of, now let the direction ratios, you know what is direction ratios? Any vector, we say direction ratios of something are any vector in that direction. Direction coefficients would be a vector of magnitude 1 in that direction. So direction, that the direction ratios of tangents at u of the members of the orths of two of the members of the orthogonal trajectories of second be denoted by, of the family 2nd be denoted by, let us denote the direction ratios of the orthogonal trajectories of the 2nd by u and dv, this small del u del v, so that these two directions are now perpendicular, so that du by dv or du dv, these two directions on the surface, and del u del v are perpendicular, orthogonal or perpendicular. Chalo, perpendicular, orthogonal, one and the same thing. Okay, now look what I have now. What I have is, let me I have started.
Not again. Let me do it. How about a family of curves? Essentially, I've got actually a family of curves in my domain. I've got a family of curves which has got certain direction ratios, another family of curves which are orthogonal trajectories of these given family of curves. And I've denoted them by this del u and del v. And then we already know the condition for these two directions to be orthogonal on the surface would be in terms of first and second order fundamental magnitudes it would be. So then we must have what we must have e du del plus f times du del v plus dv del u plus g dv del v is equal to 0. Now we know that du del v, the original direction du and dv are basically have got direction ratios minus q and minus p. So essentially they are proportional to minus q and p. Therefore since the right hand side is 0, I get this would imply e times minus q del u plus f times, let me write it, it is minus q because du is minus q plus p del u plus g into p del v is equal to 0, which after a bit of calculation I can get p minus times del u plus gp minus fq times del v is equal to 0, which now should be the differential equation of orthogonal trajectories. Now don't get mistaken by this del u and del v. Now essentially when I write a differential equation, plus q dv equal to 0 is our original family of curves that we started with. So P and Q do have continuous partial derivatives, first order continuous partial derivatives. And how about E, F and G now? Now E is basically Ru dot Ru. If I differentiate it again with respect to U or V, I would get second order partial derivatives of R. And in the beginning when I talked about the surface has to be of class derivatives. So one condition is satisfied for it to represent a family of curves. Secondly, both of them should not be zero. But
both of them cannot be together 0.